Ford Motor Company continues to improve engineering and design features, keeping us a step ahead of the competition. As Ford leads the way into the 21st century, our customers will continue to rely on Ford and Lincoln Mercury technicians to keep up with the latest diagnostic and service techniques. One of the latest steps forward is the new MTX 75 manual transaxle. This lightweight transaxle is compact and extremely quiet. Used in the all-new Ford Contour and Mercury Mystique, the 5-speed MTX 75 provides high torque capacity and easy gear shifts. The name MTX 75 describes the transaxle. MT refers to manual transmission. The X indicates that it's a front-wheel drive transaxle, and 75 millimeters is the distance between the input shaft and the output shaft. During this video, we'll look at the new tools and procedures you'll use for the MTX 75 when servicing the Contour or Mystique. But first, let's look at the transaxle itself and see how it operates. The MTX 75 uses a cast aluminum two-piece housing, much like the MTX 4 used in the Taurus show. It's a closed-end case that doesn't require any external end seals. The case splits into a clutch half and a trans half. The two-shaft design has a simpler power flow than the three-shaft design of the MTX 4. The input and output shafts run in tapered roller bearings with shimmed races to provide preload. All gears, including reverse, are bevel cut and synchronized. Gears which are not pressed onto the shaft run on needle bearings. The input shaft is driven by the engine crankshaft when the clutch is engaged. The first, second, and reverse driving gears are integral parts of the shaft. The third and fourth driving gears run on needle bearings mounted in fiber collars. The third, fourth synchronizer assembly is mounted between them. The fifth driving gear is pressed onto the input shaft and retained with a snap ring. Tapered roller bearings are pressed onto both ends of the input shaft, with races pressed into each case half. The clutch and bearing race is shimmed to provide preload for the input shaft. When a gear is engaged, the input shaft drives the output shaft. The third and fourth driven gears are integral parts of the output shaft. The remaining driven gears on the output shaft run on needle bearings mounted in a fiber collar. Synchronizer assemblies on the output shaft are located between first and second gears, and fifth and reverse gears. The pinion gear is pressed onto the output shaft and retained with a snap ring. Like the input shaft, tapered roller bearings are pressed onto both ends of the output shaft. The clutch and bearing race is also shimmed to provide preload. Unlike the MTX 4, the MTX 75 reverse idler gear is not shifted to engage reverse gear. It's in constant mesh with the reverse gears on the input and output shafts. This causes the reverse gear on the output shaft to freewheel in reverse when the forward gears or neutral are engaged. The idler gear runs on needle bearings and is positioned on the shaft by two thrust washers. The reverse idler gear assembly is retained by a bracket secured by two bolts from outside of the case. Another major difference from the MTX 4 is the design of the synchronizer assemblies. The MTX 75 doesn't use retaining rings or exterior springs to hold the synchronizers together. Instead, each hub assembly includes 3 blocker bars, steel balls, and internal springs. The spring-loaded balls and blocker bars fit into 3 slots in the hub. This arrangement keeps the sleeve lightly locked in position on the hub when a gear isn't engaged. Like other Ford 5-speed transaxles, the MTX 75 uses 3 synchronizer assemblies. As we saw before, the first, second, and fifth reverse synchronizer assemblies are located on the output shaft, and the third, fourth synchronizer is located on the input shaft. The synchronizers include one more major innovation. Beginning in mid-year, the MTX 75 will use double synchronization. By using an all-new type of synchronizer ring, there's a remarkable improvement in shiftability during downshifts. Double synchronization consists of an inner synchronizer ring, a cone synchronizer ring, and an outer synchronizer ring. The friction cone of the gear is deleted. Instead, the cone synchronizer ring has both inside and outside friction surfaces. It attaches to the gear, with the inner synchronizer ring between them. With the outer synchronizer ring, friction surface is enlarged by 100%, allowing for easier shifts. Double synchronization will be used for first, second, and third gears. The other gears will continue to use traditional synchronizer rings. The internal shift mechanism also contributes to smooth shifting. The selector shaft includes a ball and cup assembly to control the inner gearshift rod, which is positioned vertically. The other end of the gearshift rod is connected to the selector gate. 3 brass shift forks ride on 2 selector rods to move the synchronizers and engage gears. The reverse lamp switch is mounted to the internal shift mechanism housing on top of the transaxle case. Unlike other transaxles, the selector interlock is located inside the internal shift mechanism assembly. The interlock prevents a gear from disengaging until another gear is selected. A spring-loaded ball on the selector gate holds the interlock cam in one of 3 positions: first, third, and fifth gear, neutral, or second, fourth, and reverse gear. Those were the major components of the MTX 75. Before moving on, let's briefly overview the operation of this manual transaxle. Gear selection begins with the operator moving the gear shift lever, which is connected to the selector shaft. This moves the inner gear shift rod up or down to select the fork. The selector shaft also pivots the inner gear shift rod, causing the selected shift fork to engage the synchronizer assembly. Like other transaxles, the synchronizer engages the selected gear to its shaft. This causes the output shaft to rotate at the selected gear ratio. Now, please stop the tape and answer the review questions for Lesson 1 in your reference book. When you're finished, restart the tape and we'll go over the answers before beginning the next lesson. The answer to question 1 is A. The input and output shafts run on tapered roller bearings. The answer to question 2 is C. The input and output shaft bearing shims are installed between the bearing race and the clutch end of the case. The answer to question 3 is C. The third and fourth driven gears run on needle bearings. The answer to question 4 is D. The reverse idler gear also runs on needle bearings. The answer to question 5 is B. The reverse idler gear is stationary and is not shifted to engage reverse gear. The answer to question 6 is A. The reverse idler gear is positioned on the reverse idler shaft by an upper and lower thrust washer. The answer to question 7 is B. The reverse idler gear is retained on the reverse idler shaft by a bracket. The answer to question 8 is D. To select reverse gear, the fifth reverse synchronizer assembly engages the reverse gear on the output shaft. The answers to question 9 are the reverse gear and reverse idler gear. These stationary components are in constant mesh, which is different from reverse operation in other Ford Motor Company transaxles. The answers for question 10 can be found on page 1-18 of the student reference book. As with any manual transaxle, MTX 75 power flow begins with the input shaft whenever it's engaged by the clutch to the engine crankshaft. The input shaft is in constant mesh with the output shaft. When a gear is engaged, the output shaft rotates at a specified gear ratio. Power flow continues through the pinion gear, which drives the final drive ring gear and differential. The differential delivers power to the axle shafts and the front wheels. For example, let's look at the components that produce first gear. The internal shift mechanism causes the first-second shift fork to move the synchronizer forward, locking first gear to the output shaft. Now let's look at the power flow from another angle. The first gear on the input shaft drives the first gear on the output shaft, which is engaged by the synchronizer. The output shaft rotates at the first gear ratio of 3.42 to 1. As soon as the operator shifts into second, the first-second synchronizer sleeve moves rearward to engage second gear on the output shaft. The input shaft drives the output shaft at the second gear ratio, which is 2.14 to 1. Shifting up to third gear causes the first-second synchronizer sleeve to move back to neutral, and the third-fourth synchronizer is moved forward to engage third gear on the input shaft. The input shaft drives the output shaft at the third gear ratio, which is 1.45 to 1. When the operator moves into fourth, the third-fourth synchronizer sleeve is pushed rearward to engage fourth gear on the input shaft. The input shaft drives the output shaft at the fourth gear ratio, which is 1.03 to 1. When cruising at highway speed, the operator may shift into fifth gear overdrive, causing the third-fourth synchronizer sleeve to be shifted back to neutral, while the fifth reverse synchronizer moves forward to engage fifth gear on the output shaft. The input shaft drives the output shaft at the fifth gear overdrive ratio of 0.77 to 1. Selecting reverse is very similar to the forward gears. A shift into reverse moves the fifth reverse synchronizer sleeve rearward to engage the reverse gear on the output shaft. The difference is the stationary reverse idler gear. This gear is driven by the input shaft reverse gear, and now drives the entire output shaft in a reverse direction, at the reverse gear ratio of 3.46 to 1. You should be able to combine this introduction to MTX 75 operation and power flow with your previous transaxle skills and knowledge. This combination will give you a strong basis to accurately diagnose concerns in this transaxle. By considering which components are engaged when a concern appears, you should be able to narrow down the possible causes and isolate the concern. Let's look at an example. A vehicle is brought to your dealership with a shifting concern. The customer reports that the transaxle pops out of third gear. You take it for a test drive and verify that the problem really exists. You consider the possibilities and suspect several possible causes. It could be the external shift linkage, the internal shift mechanism, the synchronizer assembly, the shift fork, or the selector shaft. Which of these is the most likely cause? Which would you check first? Since the external shift linkage is the easiest check, you inspect it first and find that it's not the problem. Now, you would have to disassemble any other transaxle to continue your diagnosis, but first you consider the unique features of the MTX 75. The internal shift mechanism is in a housing you can remove without separating the transaxle case. You examine the assembly and find the cause of the concern to be a loose retaining bolt for the selector finger sleeve. The sleeve was moving on the inner gearshift rod, preventing the shift fork from fully engaging third. The bolt must be replaced. Then you can install the transaxle and test drive the vehicle to verify the repair. By considering this easy check, you avoided disassembling the entire transaxle. Carefully thinking through your diagnosis can save you a lot of time. Always pinpoint the cause of a concern without creating extra work. An understanding of the unique features of the MTX 75, along with your general transaxle knowledge, will always help you to diagnose effectively. Now, please stop the tape and answer the review questions for Lesson 2 in your reference book. When you're finished, restart the tape and we'll go over the answers before beginning Lesson 3. The answers for Question 11 are also shown on pages 2-16 and 17 of the Student Reference Book. For first gear, the first-second synchronizer sleeve is shifted forward, and the other synchronizer sleeves are centered on the hubs. For second gear, the first-second synchronizer sleeve is shifted rearward. For third gear, the third-fourth synchronizer sleeve is shifted forward, and the other synchronizer sleeves are centered on the hubs. For fourth gear, the third-fourth synchronizer sleeve is shifted rearward. For fifth gear, the fifth reverse synchronizer sleeve is shifted forward, and the other synchronizer sleeves are centered on the hubs. For reverse gear, the fifth reverse synchronizer sleeve is shifted rearward, and the reverse idler gear drives the output shaft in a reverse direction. The answer to Question 12 is B. The customer hears a grinding sound when shifting into second, but the car runs fine. The most accurate possible cause is that the first-second synchronizer assembly rearward synchronizing ring is worn and not properly engaging second gear. The answer to Question 13 is D. The transaxle won't shift into reverse, and the concern appeared suddenly. The most possible cause is that the rear half of the fifth reverse synchronizer hub teeth are worn. The answer to Question 14 is C. The customer hears a slight grind when shifting into fourth. It's likely that the third-fourth synchronizer's rearward ring is worn. The answer to Question 15 is B. In fifth gear, the fifth reverse synchronizer assembly is shifted forward. Servicing the MTX 75 requires many of the same skills you already use to service the MTX 4 and other Ford Transaxles. We'll now look at the new procedures and tools needed for the MTX 75, beginning with removal and disassembly. Refer to the Contour Mystique service manual for complete procedures. Before removing the transaxle, there are a few key steps you must take. Install the 3-bar engine support and support the radiator at the upper mounting pins. After supporting the subframe with the Rotunda Powertrain lift, remove the left and right hand engine support insulators. This allows you to remove the subframe, which you have to do before removing the transaxle. There are slight differences in the mountings for the two different engines available. Be aware of this before removing the transaxle. After removal, you're ready to disassemble the transaxle. Unlike the MTX 4, your first step is to remove the internal shift mechanism. Make sure the transaxle's in neutral. Then remove the 6 bolts and the mechanism from the trans half of the case. Use a pry lever to separate the clutch half of the case from the trans half. This procedure is the same as the one you use for the MTX 4. To remove the selector rods, lift them straight up out of the forks. Then remove the forks by pivoting them off the synchronizer sleeves. The reverse idler gear retaining bracket is mounted with 2 bolts on the side of the case. Remove these bolts and tilt the gear shafts to remove the bracket and the reverse idler gear. Now you can lift the input and output shaft assemblies out of the case together. If it's necessary to remove the selector shaft, remove the ball cup and retaining bolt. The shaft will then slide out. You'll need a special tool to remove the selector shaft oil seal. Use the shifter shaft seal remover installer. There's a new special tool to remove the selector shaft bearings from the case. Use the shifter shaft bearing remover and replacer with a hammer. Although it's not always necessary to remove the reverse idler shaft, it requires a special procedure. Turn the case over to remove the 3 screws holding the reverse idler mounting plate. Then use a brass punch to drive out the shaft. Gear shaft disassembly is similar to the MTX 4 and other Ford Transaxles, except for the pinion gear on the output shaft. After removing the tapered roller bearing and snap ring, position the gear puller under first gear. You can then use the press and first gear to remove the pinion gear. Attempting to remove the pinion gear separately by placing the tool above first gear will damage one or both gears. To remove the differential pinion pin, use a suitable tool to press it out. Shear off the retaining roll pin. Now, please stop the tape and answer the Lesson 3 review questions in your reference book. When you restart the tape, check your answers. Then we'll go on to Lesson 4. The answer to question 16 is C. The internal shift mechanism assembly must be removed first before the housing can be separated. The answer to question 17 is D. The internal shift mechanism assembly is mounted on the top of the case. The answer to question 18 is C. The transaxle housing is separated with pry levers, as with the MTX 4. The answer to question 19 is A. The reverse idler gear is held in place by tool bolts and a bracket. The answer to question 20 is B. The pinion gear on the output shaft is removed by using a press and a gear removal tool placed behind first gear. The answer to question 21 is A. The differential pinion pin retaining roll pin is removed by pressing out the pinion pin and shearing off the retaining roll pin. The tool shown with question 22 is the shifter shaft bearing remover replacer. Its tool number is T94P7025DH. Its function is to remove and install the selector shaft bearings. Whenever bearings or bearing races are removed or replaced on the input shaft, output shaft, or differential, preload must be measured and adjusted. Do this when service is complete and the transaxle is ready for assembly. This lesson covers the new and critical procedures for setting preload on the MTX 75. There are 4 main steps. First, install the specified service shims under the bearing races of the clutch case half. These shims allow you to start your measurements at a predetermined value. Second, measure and record the end play. Third, use your average measurement to calculate the correct shim thickness. Finally, install the required preload shim. Use the stator and driven sprocket bearing remover and the impact slide hammer to remove the bearing races from the clutch half of the transaxle case. Remove the shims, then install the specified service shims from the replacement shim kit. You'll need to use heating and cooling techniques. Follow this procedure to prevent premature wear of the case and to provide an accurate measurement of preload. First, cool the outer bearing race to 46 degrees Fahrenheit. Then, use a temperature pencil to mark the bearing race area on the clutch half of the transaxle case. Heat it to 176 degrees Fahrenheit with the Rotunda heat gun. When the temperature mark melts, gently tap the bearing race into the clutch half of the case using the new bearing cup replacer, the driver handle, and a hammer. Repeat this procedure for each bearing race. Be very careful when installing the races, or you may severely damage the case. Make sure all tapered roller bearings are oil-free and that fourth gear is engaged on the input shaft. Finally, install the input shaft, the output shaft, and the differential. While assembling the case halves, use 2 bolts to install the shim selection tool adapter. Tighten all bolts to 27 Newton meters. Next, place the transaxle upright in the holding fixture. Now you're ready to begin taking measurements. First, use the pinion spline socket to settle the input shaft. Turn the shaft back and forth a quarter turn, about 20 times. Mount a metric dial indicator at the clutch end of the transaxle. Position the indicator on the input shaft and set it to 0. Place a suitable lever under fourth gear through the selector housing hole. Lift the input shaft and note the reading. Repeat this procedure at least 3 times and record each measurement. When you're finished, calculate the average value. For example, say you take 4 measurements, 26 hundredths of a millimeter, 24 hundredths of a millimeter, 23 hundredths of a millimeter, and 23 hundredths of a millimeter. Add them together, and the total is 96 hundredths of a millimeter. Since you took 4 measurements, divide this by 4. The result is 24/100ths of a millimeter, which is your average input shaft end play. Next, measure the end play of the output shaft. Install the measuring fixture at the internal shift mechanism hole and place the plunger on top of fourth gear. Settle the output shaft with the pinion spline socket, turning it back and forth about 20 times. Install the dial indicator and position it under the plunger arm of the measuring fixture. Make sure it's set at 0. Lift the output shaft with a suitable lever and record your measurement. Repeat this procedure at least 3 times, and then calculate the average output shaft end play. Finally, measure the differential end play. Settle the differential by turning the input shaft back and forth with the pinion spline socket, pushing down on the differential. Install the dial indicator over the differential and set it to 0. Make sure it contacts the carrier housing and not the bearing. Next, attach the valve spring compressor set and the additional shim selection tool adapter to the adapter that was previously installed. Use a breaker bar to lift the differential and note the end play reading. Repeat this procedure at least 3 times. Once again, calculate the average end play. Now you have the information you need to calculate the thickness of the required preload shims. Refer to your reference book or the service manual for the chart to guide you through these calculations. You will need to add 3 numbers to select the correct preload shim. The first number is the thickness of the service shim you used. This is a specified number listed in the service manual. For the input shaft, the specified service shim is exactly 1 millimeter. Next, add the average end play value you measured. In our example, this was 24/100ths of a millimeter. The third number is the specified preload value. This number is determined by the manufacturer and can never be modified. For the input shaft, it's 1/10 of a millimeter. Add these 3 numbers to find the thickness of the required preload shim. In our example, the total is 1.34 millimeters. Now, select the correct preload shim. Only 1 shim can be chosen per component. Shims are available in specified increments within specific ranges. If the shim you need is not one of the sizes available, use the next lowest shim value. For the input shaft, the range of available shims is 1.27 to 1.71 millimeters. The required shim for our example falls in this range, but no shim of this size is provided. The next lowest shim size is 1.33 millimeters, so this is the preload shim you should select. Never raise the required preload shim value. Doing this can cause damage to transaxle components. The procedure for calculating the output shaft and differential shims is identical to our example. The numbers, of course, will all be different, but the math is the same. Always refer to the Contour Mystique service manual for specifications. Refer to your self-study student reference book for this course for more examples and practice with these calculations. After selecting the correct shims, remove the special service tools from the transaxle, remove the transaxle from the holding fixture, and separate the case halves. Remove the bearing races and service shims, and install the selected shims and bearing races using MTX 75 heating and cooling techniques. Now, please stop the tape and answer the review questions for Lesson 4 in your reference book. Once again, we'll go over the answers before beginning the next lesson. The answer to question 23 is B. For measuring input shaft, output shaft, and differential bearing preload, the service shims are installed behind the bearing races in the clutch half of the case without any other shims. The answer to question 24 is D. For setting input shaft, output shaft, and differential bearing preload, the required preload shims are installed in the clutch half of the case after removing the service shims. The answer to question 25 is A. Input shaft, output shaft, and differential bearing preload is measured with the transaxle positioned with the clutch end up. For question 26, the average input shaft end play value is 26/100ths of a millimeter, and the required shim is 1.36 millimeters. Since a shim of this size is not available, you should install the next lowest size shim, which is 1.35 millimeters. The average output shaft end play value is 39/100ths of a millimeter, and the required shim size is 1.64 millimeters. The available shim to be installed is 1.63 millimeters. The average end play value for the differential is 46/100ths of a millimeter, and the required shim size is 1.98 millimeters. The available preload shim to be installed is 1.95 millimeters. For question 27, the average input shaft end play value is 37/100ths of a millimeter, and the required shim is 1.47 millimeters. Since this is an available shim size, you should install a 1.47 millimeter preload shim. The average value for the output shaft is 45/100ths of a millimeter, and the required shim size is 1.70 millimeters. Since this size is not provided, select the next lowest available size, which is 1.69 millimeters. For the differential, the average end play value is 25/100ths of a millimeter, and the required shim size is 1.77 millimeters. The available preload shim you should install is 1.75 millimeters. In this lesson, we'll conclude our examination of the MTX 75 by looking at the new tools and procedures needed to assemble and install the transaxle. The service manual covers complete step-by-step procedures, so we'll again focus on the differences from other Ford transaxles. Input and output shaft assembly is similar to the MTX 4. Although the pinion gear removal is unusual, installation is a common press procedure. Always install new snap rings. Assemble the differential carrier using new shims, and use a new roll pin to retain the pinion pin. Use the bearing cone replacer and driver handle to install the upper and lower bearings. Use the new shifter shaft bearing remover and replacer and a hammer to install the selector shaft bearings in the case. Install the innermost bearing first. Make sure it's flush with the case. If the bearings are not positioned correctly, they may wear prematurely and possibly affect the shift quality of the transaxle. If the reverse idler shaft was removed for service, use the Rotunda heat gun to heat that area of the outside case to about 176 degrees Fahrenheit. Apply gasket eliminator to the mating surface of the reverse idler shaft retaining plate. Then, position the shaft in the hole and drive it into position using the mounting screw for a guide. When the case cools down to room temperature, tighten the 3 retaining screws to 24 Newton meters. Do not install the reverse idler gear at this time. The heating and cooling techniques shown earlier are needed to install the bearing races in both halves of the transaxle case. As we saw in the last lesson, races in the clutch half are installed with selectable preload shims. After tapping in the races, you may install the reverse idler gear assembly. First, place the lower thrust washer in position. This position is critical. If the tab is not correctly aligned, the gear will not seat properly. Place the needle bearing on the idler shaft. Before installing the gear, fit the input and output shafts together and install them in the case. Tilt the input and output shafts to install the reverse idler gear on the idler shaft. Next, install the reverse idler retaining bracket. Make sure the upper thrust washer tab fits into the slot on the bottom of the bracket. Apply gasket eliminator to the retaining bracket mounting bolts before tightening them. After installing each shift fork onto the corresponding synchronizer assembly, insert the selector rods. Ensure that the rods are seated in the indentations in the case. If seated incorrectly, the forks won't properly engage and the transaxle may not shift at all. To assemble the case halves, apply a 0.2 millimeter bead of gasket eliminator to the mating surface of the trans half. With the case halves assembled, install the internal shift mechanism housing. Ensure that the ball on the selector shaft is seated in the ball cup by trying to shift the linkage by hand. If the ball and cup are not seated properly, the linkage will move freely. Finally, use the differential drive shaft seal replacer, the driver handle, and a hammer to install new axle shaft seals. Complete transaxle installation procedures are covered in the Contour Mystique service manual. Remember these 3 key steps during transaxle installation. First, use the frame alignment pin set to align the subframe for installation. Second, perform an engine alignment if the front engine mount was loosened during service. And third, remove the 3-bar engine support only after the transaxle and the right and left-hand engine support insulators have been installed. Don't forget to add new fluid. The MTX 75 is lubricated with synthetic Mercon multi-purpose automatic transmission fluid. Its fluid capacity is 2 quarts and 26 ounces. 2% of the fluid, however, must be friction modifier. Be sure to include 2 ounces of friction modifier with the trans fluid. With the transaxle installed, you must adjust the shift linkage. After removing the upper shift boot, lift the other boot up on the shift lever. Install the gear lever aligning tool and lock it in place. Raise the vehicle. Make sure the transaxle's in neutral. Then tighten the clamp bolt on the linkage to 16 Newton meters. Now, please stop the tape and answer the review questions for Lesson 5 in your reference book. After checking your answers, we'll begin the final lesson. The answer to question 28 is D. Installation of the reverse idler shaft requires heating of the outside of the case around the shaft area. and application of sealer to the mating surface of the shaft mounting plate. The answer to question 29 is B. The reverse idler gear lower thrust washer tab is installed in a specific slot of the trans half of the case. The answer to question 30 is A. Subframe installation requires the subframe to be aligned to the vehicle with the frame alignment pin set. The answer to question 31 is C. After installing the transaxle, fill it with Mercon multipurpose automatic transmission fluid and 2% friction modifier. The answer to question 32 is D. With the transaxle in the neutral position, adjust the shift linkage by installing the gear lever aligning tool and tightening the clamp. The operation of the Contour Mystique hydraulic clutch system is similar to other hydraulic clutch systems used in Ford Motor Company vehicles. The locations of the components, however, are unique. Unlike other systems, the clutch master cylinder is mounted under the instrument panel. Master cylinder line connections extend through the bulkhead. This design helps control leakage and prevent in-vehicle spills during service. Fluid for the hydraulic clutch system is supplied by the brake master cylinder reservoir. A fluid feed line connects the rear of the reservoir to the clutch master cylinder. Also, unlike other systems, the slave cylinder is mounted on the transaxle assembly in place of a release bearing. The slave cylinder consists of a hydraulic actuator with a release bearing and an input shaft oil seal. Because this hydraulic clutch system operates like most others, diagnosis is also largely the same. Be thorough, though, when checking for leaks. Since the slave cylinder is mounted in the transaxle, any leak from the slave cylinder will take longer to notice and may appear to be a different type of fluid leak. Remove the clutch master cylinder after removing the lower instrument panel and pedal carrier mounting. Also, service the slave cylinder as an assembly. To replace the slave cylinder, you must remove the transaxle. Follow the same procedure to bleed the system as for previous systems. Loosen the bleeder screw on the slave cylinder after installing a suitable hose and adding brake fluid. Depress the clutch pedal as many times as needed until air is eliminated from the system. Make sure the brake fluid reservoir remains full at all times. Now, please stop the tape for the final set of review questions. Restart the tape for the answers and the conclusion of this self-study course. The answer to question 33 is A. The clutch master cylinder is mounted to the clutch pedal bracket under the instrument panel. The answer to question 34 is B. The slave cylinder for the clutch is mounted in the transaxle in place of the release bearing. The answer to question 35 is B. To service the clutch slave cylinder, you must first remove the transaxle. The answer to question 36 is A. To service the clutch master cylinder, you must first remove the lower instrument panel. This concludes our look at the MTX 75 manual transaxle for the Ford Contour and Mercury Mystique. Remember, for specific service procedures, always refer to the 1995 Contour and Mystique service manual.